Hello everyone. It's a great pleasure to be part of that series of webinar this afternoon. I'll be talking on the monitoring and recommendations regarding measurements of the chemical composition of particulate matter, whether it is online or offline, and also all the added values that we can perform and get from these kind of measurements. So I am a researcher at LSE, located near Paris, and my area of expertise is obviously the chemical composition of PM. This presentation was prepared with the great help of Olivier Favez from Ineris, and also I want to acknowledge all the people who provided material from the RI-URBANS service tools, for which actually was very useful for preparing that presentation. As a quick introduction, I would like to quickly say that particulate pollution is complex. First, by virtue of the multitude of emission sources and the diversity of their chemical fingerprints. This is not an exhaustive list of the sources of aerosols in the atmosphere, but we can actually separate these into two different kind of sources. First, natural sources like sea salt, dust, forest fires, volcanic activities, as well as primary biogenic emissions. Rather than in urban areas, people are more exposed to anthropogenic sources like traffic, which can be separated into exhaust and non-exhaust emissions, wood burning, like residential wood burning heating, also any kind of energy, any kind of emissions related to energy, like coal combustions, for instance, as well as specific industrial activities. And also I'd like to mention agriculture, which can actually be an emitter of precursors of secondary aerosols. It is also complex by virtue of their physical and chemical properties. You can see here on the left that the shape of the particles can vary a lot. For instance, sea salt have that really nice cubic shape, rather than soot are more in a form of small aggregates of carbon, like atoms and molecules. These shapes can vary in size and also in terms of mixture. This is represented on the right side of the slide here, that throughout their atmospheric process within the atmosphere, from the emission to the actual measurement, the status of the mixture of the aerosols can vary over time, going from an external mixture here to a mixing state, which can be a bit more complicated in terms of characterization. It is also very complex due to the multitude of transformation processes and meteorological parameters. We can for instance, note that we can have transport of pollution over large geographical scales, and also physical processes like wet and dry deposition, which can play a role on the residence time of the aerosols in the atmosphere. Following different meteorological conditions like sun or sunlight, and also the initial composition of the atmosphere and actually what's in there, we can have a lot of reactions forming or enabling the formation of secondary pollutants, which add another layer of complexity. The the graph on the right actually shows the different sizes of the aerosols from the nanometer scale to around 10 nanometers. And so this is all linked to the different sources, to the different processes, and everything is really complex when we measure that at some sites. Talking about quickly also the new European Air Quality Directive, which I guess you may be comfortable with, but just to present here that that new Air Quality Directive confirms or introduces the analysis of specific PM10 or PM2.5 components, such as metals, polyaromatic hydrocarbons, levoglucosan, elemental and organic carbon, as well as PM2.5 speciation at supersites. So these you have three tables here that present the pollutants to be measured at monitoring supersites. The first one, bottom left, present the pollutants to be measured at monitoring supersites at urban background locations. So we still have the confirmation of measurements of components like BAP or some metals like cadmium or lead and nickel, but also the chemical composition of PM2.5. This is also to mention that in table 2, there's the pollutants to be measured at the supersites at rural background locations. And in table 3, it's the pollutants to be, or variables to be measured at monitoring supersites at urban and rural background locations, if not covered by the two aforementioned tables. And what we can see in this third table is that levoglucosan is the only new chemical component to be introduced from filter measurements at urban and rural background. Why levoglucosan? Is that it is so levoglucosan and its isomers are emitted from the combustion of amycellulose, and it is actually a specific tracer for biomass burning. Although its reactivity and residence time in the atmosphere may vary, it is still a very good tracer of biomass burning, and so that's why this molecule is being added to as recommended in the new Air Quality Directive. So now, talking about the speciation of aerosols from offline measurements, I would like to present some of the recommendations on sampling and measurements. The aim here is to be able to assess the possible contribution from long-range transport of pollutants and also support source apportionment analysis and for the understanding of specific pollutants such as PM. The good thing with sampling and measurements from offline for offline PM speciation is that it is well framed with standard protocols and methods which can help anyone implementing this kind of measurements. For the sampling, so there's here listed the acronym of the standard method for sampling, but quickly, PM sampling should be performed using low volume samplers at around, for instance, 2.3 millicurie per hour. But high volume sampler may still be used for monitoring purposes and also ongoing quality control. For measurements, to be able to have a comprehensive overview of the chemical composition of PM, you actually need a lot of different kind of analytical methods. And the good thing as well is that there are lots of specific analytical reference protocols that are listed here that can help to guide the implementation of such kind of measurements. For instance, everything related to the measurement of lead, cadmium, arsenic, and nickel is framed in the standard protocol, as well as measurements of the major ions like nitrate, sulfate, chloride, ammonium, sodium, potassium, etc., deposited in filters, and also ECOC concentrations from filter samplings. And also to mention that there is a reference document now recently published for levoglucosan measurements. So I'm not going to detail here all of these protocols, but you can actually find all the necessary information in these standard protocols. I would like here to mention the our urban service tool for PM offline speciation. This is also where because you can find a description of the different reference protocols that I mentioned. But I wanted to have a quick slide on the main findings of their service tool that has been written for our urbans, and that service tool is actually now online. I will show the link to the document at the end of the presentation. Here it's the graph here is a phenomenology study of PM10 bound trace elements in the urban atmosphere of urban areas in Europe. And what is actually striking is that there is a lack of PM chemical composition data in Central and Northern Europe. This really strikes the eye, and it's interesting to see on the right side hand of the slide that there is some kind of differences in terms of trace element contribution to different kind of environments, whether it is urban here, traffic here, and rural background, for instance. So there's still need for harmonization in measurement techniques and data reporting among the different member states. But also there's a critical need to expand PM speciation studies for advanced air quality assessment, including source apportionment. Talking about source apportionment, how do we do it from the chemical composition data? One of the most commonly used technique to perform source apportionment is receptor model, especially positive matrix factorization. Positive matrix factorization actually relies on this one simple equation where the input data represented here as X is factorized into two different kind of data, F and G, regarding factor source profiles and temporal contributions, and E is the residual of the analysis. So in order to perform good and robust PM source apportionment from offline chemical composition, you first need to have the analysis of the major component of PM10, which is, for instance, ECOC, major ions, and also any kind of elements that contribute largely to the PM10 mass. Also, what is really helpful in terms of receptor modeling, especially with PMF, is that you need information from tracers of specific sources. like major trace elements, including traces of dust and different industrial traffic and combustion sources, like aluminum, calcium, iron, nickel, vanadium, for instance, among others. And also biomass burning traces like sugars, for instance, levoglucosan, or PAHs. Also for the analysis of additional PM components, for advanced air quality assessment, you may need further chemical characterization to have source apportionment of cost-effective action plans, epidemiological and toxicological analysis in order to identify the most harmful PM components and sources. So here is a paper describing the key chemical information to introduce into a source apportionment analysis, and one of the main finding or the main take-home message of that article is in the paper, in the title, is that the uncertainty linked to the source apportionment output is directly linked to the choice of input of the chemical components. This study has been based on the chemical characterization and dedicated source apportionment. You may want to mute your mic, sorry. At 3 different sites in Europe: Barcelona, Milano, and Grenoble in France, and playing with the different variables and chemical constituents has enabled the recommendations. Some recommendations are of what kind of variable to use for source apportionment. As a summary, as I said earlier, at least ECOC and major ions, elements, and analysis of biomass burning tracers should be mandatory for, let's say, the main sources of PM10. If ionic chromatography measurements include MSA, which is methyl sulfonic acid, and oxalate, it may lead to further determination of the marine SOA fraction traced by MSA, and to roughly apportioned HSOA traced with oxalate. Dedicated HPLC pad measurements are really helpful for the measurements of sugar alcohols, especially ribitol and mannitol. And these components can lead to the further determination of primary biogenic emissions, which can actually contribute to a substantial fraction of PM at some sampling sites, especially from, let's say, spring to late autumn. Refined PMF analysis may include the determination of further sources depending on the tracers you can have at your disposal. It can be molecular tracers of secondary biogenic emissions, which can be measured by GCMS, LCMS, or any kind of analytical devices or techniques. Also the inclusion of different kinds of PAH measurements may lead to some improvements in the determination and quantification of combustion sources, but precaution needs to be yeah, don't know how to say that, but they may need to have a bit more caution when injecting a lot of PAH variables, since these species can come from many various origins. And also the inclusion of species like high alkanes may lead to some improvements in organic source of determination, especially print debris, but also results should be considered with caution. Other recommendations for filter-based PM source apportionment is the use of the PMF US EPA version 5 software, which you can download here with the link. And also, in order to optimize the PMF analysis and to evaluate the performance of the results, you can actually use these two guides listed here, which are at your disposal to in order to get robust results of source apportionment. Now talking online PM speciation. There is no sense standards, but regarding non-refractory submicron chemical species, what is called NR-PM1, we can use rather simple but robust aerosol mass spectrometers, ACSMs here, which can there's a picture of these two instruments here. They're widely used now for near real-time measurements of non-refractory PM1 or PM2.5. And the components that are measured are organic aerosols, sulfate, nitrate, ammonium, and chloride. Although there is no sense standards for these measurements, they are recommendations and standard operating protocol produced by ACMCC and the Cost Colossal Action. Talking about ACMCC is a unit of the CAIS-ECAC Calibration Center of Actris, and the role of ACMCC that is led by Olivier Favez, and I'm the deputy of that unit, is developing SOPs for the online measurements of chemical composition of PM, and also to perform inter comparisons, do some trainings, the development of innovative services, the evaluation of new technologies, among others. Regarding black carbon can be indirectly measured by absorption, and this can be done with ethylometers. And from ethylometer measurement can be derived mass concentration of EBC. I'm not going to talk a lot on the black carbon and ethylometer because Marco Podolfi is going to present that in much greater detail than me. So stay tuned for his presentation. And for trace metal elements, there are recent instrumentations that allow, through X-ray fluorescent techniques, the online determination of trace elements. And so there's an European working group called ROCSI, whose role is to design a future SOP and recommendations for the implementation of such kind of measurements. Presenting here the urban service tool for PM online speciation. Here's the just a map of where measurements are being performed in Europe. It is also not it may be not comprehensive here of all the sites having ACSM measurements, but it gives a rough idea of where measurements are being performed. So we have compiled within URBANS around the ACSM data from 35 sites in Europe, mostly urban background sites, 26 sites, and also 5 suburban sites, 3 traffic, and 1 regional background sites. You can see here on the right side hand of the slide that the measurements have started um, for let's say recently. The history of ACSM data is rather short, but more and more sites have now multi-year information, and that can be really helpful to understand the temporal variability of the chemical composition of PM at this kind of sites. Also, one example that is, I think, really relevant for today's presentation is that ACSM measurements and ACSMs and ethylometer measurements are already established in the French air quality monitoring network. This is coordinated by the French Central Laboratory of Air Quality Monitoring. And you can see here a map of the different sites where ACSMs and ethylometer instruments are implemented. And you can also see that it actually started in 2015, and the latest measurements are in Paris, I think, in traffic, in a traffic background. So this is these measurements are really part of the air quality monitoring stations, and you can see here some of the chemical composition and the contribution of the different constituents across the different sites. This data is part of a data paper that is available on the ESSD, and you're very much welcome to go see the paper of Asna Sebastian describing this very valuable data set. So this is an example of implementing this kind of measurements, innovative measurements within air quality monitoring network. One of the added value of having these measurements is to allow to characterize PM pollution episodes in near real time when you combine ACSM and ethylometer measurements. This is an example in Paris, taking the data of Cirta, which is a suburban station located southwestern Paris. During the really specific episode of December 2016, with some, we've been able from ACSM and ethylometer measurements to estimate some of the sources, especially combustion sources, in dark and dark green here, compared to secondary aerosols in secondary organics in light green, and secondary inorganic in blue and red. So this is actually can be useful for air quality monitoring networks to characterize in near real time PM pollution episodes and to provide information on the characteristics of the pollution episode that is currently occurring. Talking about now of source apportionment using ACSM data. Here we are not talking of organic aerosol. I'm sorry, we're not talking about PM source apportionment, but organic aerosol source apportionment. So we're still using PMF, still the same simple equation, but the data are different. We don't use the chemical composition of data. We use the mass spectra data of organic aerosols to estimate the sources of organic aerosols. So the typical outputs of this kind of analysis is the determination of the contribution of the different sources, primary sources of OA, like traffic, like biomass burning or cooking, which can occur in, let's say, urban environments, and also the characterization of secondary organic aerosols. There's a specific approach for organic aerosol source apportionment, especially for long-term data. There are two complementary methodologies: seasonal and rolling. There's an example here, an illustration here of the two methods. The first one is just a separation of the data into the different seasons, whereas the other one is actually the window that shifts along the analysis, which enables to take into account intra-seasonal variability. So although rolling PMF can have enhanced performance in terms of relevance, it is, however, very recommended to perform seasonal PMF before applying a rolling approach. Other recommendations that are very technical, so I'm not going to detail these, is to inject a priori information into the source apportionment to better guide the algorithm towards reasonable solutions. Bootstrapping can be helpful to evaluate the stability of the solution, and also collocated measurements that can act as tracers for specific sources or processes are really helpful to really test the relevance, the atmospheric relevance of the solution. This is an example of the outputs that we can have at different sites in Europe. On the left here is the contribution of different sources. So typically what is green, dark and light green are secondary sources, and the other colors are primary sources. And you can see the variability in terms of contribution of primary and secondary sources, and also the presence of specific sources, for instance, peat burning related organic aerosols in Ireland, or specific where is it here, amine related organic aerosols in Barcelona, which may be related to industrial activities. And from there, you can calculate the annual variability of the different sources, which you can see here, where secondary organic aerosols have the highest contributions during warm seasons, and biomass burning organic aerosols actually contribute significantly to organic aerosols during the cold season. For online trace metal measurements, here is a compilation of 23 data sets from 17 sites in Europe. These are mostly urban background sites, and the data sets are composed of some month to multi-year data, which the data coverage is actually detailed here. So this is a nice example, a nice illustration of the variability of the elemental composition of PM10 and PM2.5 at the different sites, highlighting the need and the interest of these kind of measurements at urban background locations.
Okay, Jean-Luc, we were looking to come to a close soon, please.
Oh yeah, sure. Sure. In terms of source apportionment using online trace metal measurements, here's an example of the different source contribution that you can get. And also, I want to mention that combined source apportionment approaches can provide further insights of source contributions in PM, but this is still an area of research. And I want to finish by geographical origins, because the knowledge of the pollution sources is essential for mitigation policies. But the knowledge of the geographical origins is also very important, especially for long-range transport. So this is an example of trajectory analysis performed in the east of France here in Metz urban area, and we have been able to locate the dust source identified by PMF related to areas in Africa, and also the sulfate-rich source identified by PMF is related to emission locations in Eastern Europe, especially Eastern Germany, and also areas like Serbia, which are well-known emission zones of SO2. So this, I just wanted to highlight that this kind of analysis can be very useful and very complementary for source apportionment. So thank you for the attention, and also I'd like to mention that the service tool document for offline and online chemical characterization of PM is available online since very recently. Thanks a lot.